Welcome back to Machine Learning Guide. I'm your host, Tyler Ranelli. MLG teaches the fundamentals of machine learning and artificial intelligence. It covers intuition, models, math, languages, frameworks, and more. Where your other machine learning resources provide the trees, I provide the forest. Visual is the best primary learning modality, but audio is a great supplement during exercise, commute, and chores. Consider MLG your syllabus with highly curated resources for each episode's details at ocdevel.com/MLG. I'm also starting a new podcast which could use your support. It's called Lefner's Life Hacks and teaches productivity-focused tips and tricks, some which could prove beneficial in your machine learning education journey. Find that at ocdevel.com/LLH. You're listening to Machine Learning Applied. In this episode, we're going to talk about Docker. Now, Docker is a technology that lets you run software on your computer, an operating system on your computer, okay? Like an entire operating system packaged up into a little package that is running inside of your, what we call the host operating system, is running a guest operating system. So if you are developing on Windows or Mac, you can use Docker to run Ubuntu, Linux, or Windows or Mac inside of your host machine. Now, you may be familiar with this concept. If you're not already familiar with Docker, you might already be familiar with the concept of virtual machines or virtualization. It's the same thing basically, but technologically different. A virtual machine does the same thing. It allows you to run an operating system inside of your operating system, Linux inside of your Windows, but it is technologically different in that, in a few ways that are important to us as developers. The first way that's important to us is that it has limited access to the host resources. Namely, it can't access the GPU, which we use all the time as machine learning engineers for machine learning projects. And another big pain about virtual machines is that you specify what resources they allocate and use up front. So you tell a virtual machine like VirtualBox or VMware, these are two popular virtual machine technologies, you're going to be using 5 gigs of RAM and 2 CPUs in advance. And now it has those allocated, it pulls those aside for use itself. And your machine, your host machine, can no longer access those resources, which sucks. So if your guest machine, the virtual machine, is not even using any of these resources, then it's still allocated away from your host machine and can't be used. Big downfall. Well, Docker and this whole containerization movement mitigates a lot of these technical difficulties through a lot of incredible technology that they've really spent a lot of man hours over the years improving, and so those two things are mitigated. The first being that Docker can access your GPU. It can, which is fantastic. So now you can write and run your machine learning projects inside of a Docker container that accesses your GPU to run these machine learning algorithms, and it doesn't matter what your host operating system is, be it Windows or Mac or Linux. Another thing being that Docker only uses the resources it needs from the host operating system. So you can run your desktop and play VR games, and use half the GPU for that. And you won't have resources pre-allocated to your Docker container that you can't then use on your host operating system. These are the obvious benefits of using containerization, but I'm going to step away from Docker for a bit to motivate some of the other bigger, more essential benefits that Docker provides. We're going to stop talking about Docker for a bit, and we're going to talk about your traditional setup when you're setting up your local host, your local development environment. You're a machine learning engineer, and you're writing everything in Python. Okay, what do? First, you select your operating system. Which operating system are you going to be running on? The most obvious choice is Ubuntu Linux, and because most machine learning packages are Ubuntu first class, they support Ubuntu always, and any support for Windows or Mac are sort of afterthoughts, second class citizenship. Even non-Ubuntu Linux distributions, Debian's fine because Debian and Ubuntu have so much in common that they'll usually what will work on Ubuntu will also work on Debian. But Other distributions may suffer from second-class citizenship when it comes to machine learning Python packages. So your obvious choice is Ubuntu. So you install Ubuntu. It's kind of a bummer, because you want to play video games, right? Or the rest of the Ubuntu desktop experience really is subpar to Windows or Mac as a desktop experience. Personally, I think so. Some other Ubuntu primary users might not think that that's the case, but I personally don't like the Ubuntu desktop experience quite as much. And games, man. I want to play video games. So what do? You dual boot Windows and Ubuntu, and you just deal with it. Oh, well. You have your Ubuntu environment. What do? You first thing, you set up CUDA and cuDNN. CUDA and cuDNN. CUDA is the NVIDIA library for GPU, matrix algebra, and all that math stuff that happens in TensorFlow, scikit-learn, and PyTorch. It happens through CUDA. CUDA is the API that lets these libraries run fast math that is related to machine learning on the GPU. Your NVIDIA graphics card runs its math through the CUDA API to the machine learning library. And then you also set up cuDNN, CUDNN, and that's the neural network API that sits on top of CUDA. CUDA is just general mathy architectural stuff. Access to the GPU. cuDNN is that plus neural network overlays, things that make writing that type of math for neural networks a little bit easier to work with, that TensorFlow and PyTorch tap into. Well, TensorFlow uses the latest version of TensorFlow as of today, November 7th, 2020. The latest version of TensorFlow uses CUDA 10.1 and cuDNN 7. And the latest version of PyTorch prefers CUDA 10.2. Well, that's kind of a bummer. Well, how do you deal with that? How do you deal with the incompatibility? Well, the nice thing is that PyTorch allows you to use 10.1. You can use an older version in PyTorch. You just have to install a specific version of PyTorch which runs optimally on that CUDA version. So you install CUDA 10.1 and cuDNN 7 on your Ubuntu operating system, and then you pip install TensorFlow and that specific version of PyTorch which supports CUDA 10.1. And then you pip install all the other packages that you require for your project. Scikit-learn, pandas, NumPy, all those things. Cool, you write your project, everything's fine. Now it comes time to deploy to a server. You need to put your machine learning model, and some web API for accessing that model through the client. Like in my case, Nothi's machine learning models run on a separate AWS instance, which we'll talk about in a bit. And then the server, the Python API backend, runs on another AWS instance. If you were to set things up manually the way we're going through this process, you would have to create 2 EC2 instances. You'd have to manually spin up an EC2 instance with an Ubuntu AMI, go through the whole steps again of installing CUDA 10.1 and cuDNN 7, etc. It's just a nightmare. It's just so much work. Also, you have a new project. You have a new client. They say, actually, we're using a different version of CUDA, cuDNN, and PyTorch and TensorFlow. Now, you're screwed. You can only support one CUDA version and one cuDNN version on your operating system. Wow, okay, you're really in high water. Let's step all the way back. That was not the right way to go. That was not the correct approach. Let's try a new approach. Anaconda. You're still on Ubuntu, but you didn't install CUDA and cuDNN yet. Anaconda is a Python environment manager, which allows you to install multiple versions of Python, Python 2.7, Python 3.5, side by side. They can coexist on the same operating system. And within those Python environments, you can install specific packages. Okay, so Python 3.5 environment wants this version of TensorFlow and that version of PyTorch, and this version of CUDA and this version of cuDNN, and any other specific versions of Python packages you might need. Then you've got your other client. You're working on this other project. Okay, you clock out of project A, and you're going to clock now into project B. You switch to your other Anaconda environment, and now you have a different version of Python, a different version of TensorFlow and PyTorch and all these things. Now, there is a thing out there called pipenv, or Python env, PyEnv, I can't remember which it is. which allows you to have multiple versions of Python and multiple packages within those environments. But what it doesn't provide to you that Anaconda does is also management of system installs, not just the Python packages themselves, but system installs. And in particular, in this example that we're creating, CUDA and cuDNN. Those are system installations. You manually download those from the NVIDIA website and you install them into your system. You go through and you set up some environment variables and you put some files into these like user lib directories and stuff. That's nothing to do with Python. That's everything to do with operating system. So one nice thing that Anaconda provides that pipenv doesn't provide is the management of system application installations, including CUDA and cuDNN. And it manages these for you automatically as dependencies to specific Python applications that you're installing. So if you were to install the PyTorch and TensorFlow packages through Anaconda, they would install for you automatically, or there may be some other flag or additional thing that they specify in the how-to that would automatically set up the right versions of CUDA and cuDNN that they need. All right, so that's a huge improvement over our previous setup, a huge improvement. Now we have siloed environments, including the correct versions of CUDA and cuDNN, and TensorFlow and PyTorch and any other Python packages needed on a different project-by-project basis. Very nice. But we still face the problem. We got to deploy this to the internet, to an Amazon EC2 instance. We still have to spin up an AWS instance, install Anaconda, and download the code for our project, set up the configuration.json files and environment variables, and open up ports and all these things. We basically have to replicate the entire environment setup we performed on our local host, on our local Ubuntu dev environment. We have to replicate that whole process in the cloud. And every time we make changes to our local environment setup, if we change some aspect of the environment setup, I'm not talking about pip packages, but the environment setup, we'll have to go to the EC2 instance and make sure we replicate that change there too. So this is a problem. Anaconda takes us halfway there, but it does not take us all the way there. So that's where Docker comes in. Docker is incredible technology. Docker lets you specify in a file how a guest operating system will be set up. Now, these aren't AMIs or Amazon machine instances. These aren't like image ISO files that you download from the internet, which would have been the case previously with VirtualBox. These aren't image identifiers that then go and download some binary file that you start from, but then you have to continue the environment setup manually yourself and then save that away as an ISO file. This is the old way of virtual machine management. No, these are code files. These are text files that you say, install Ubuntu 1804. Install CUDA 10.1, install cuDNN 7, install TensorFlow this, install PyTorch that, download this GitHub repository, make that your primary directory that you're going to be working from, and run this code as the main line of code that we're going to be running for our project. That's the entry point directive. So Docker running locally will look at this Docker file that you create in text format. It's a file with code in it. There is this Docker language that you have to familiarize yourself with. I won't say it's not a steep learning curve. It is a pretty steep learning curve, but it's well worth your time. You specify this code file called a Docker file that tells the Docker system exactly how to create a full-fledged guest operating system to run on your host with all of the required system dependencies, including CUDA and cuDNN, including the operating system, including other operating system dependencies you may need, like Postgres database, or at least the Postgres client, which might be connecting to a remote database server, and any pip packages you need to install. And then you tell it to expose some port 80, port 8888, port 3000. These are common ports. These will be the ports on which you access whatever's running on that guest operating system, be it a Python API server on FastAPI or a machine learning model that's exposing its results over a port. Or you don't need to expose the port. You dive into your guest environment's shell, like Bash, using your own terminal, the command for that is like docker exec your environment bash. Now you're inside of your operating system, your guest Ubuntu operating system. You can actually do all your code from there, or run your commands, run your machine learning scripts and stuff like this. So benefit one that Docker gives us: no operating system environment setup. Okay, you don't have to set up CUDA and cuDNN. I know I keep mentioning those two installations, but they're such a doozy. If you've been doing machine learning engineering for a while, you get where I'm coming from. Setting up CUDA and cuDNN is such a freaking pain in the butt. It's such a pain in the butt. It's not that the setup is hard. It's that you're going to hit issues. Always. You always hit issues. I don't know why. Sometimes it's like TensorFlow and PyTorch version compatibility in what they expect of the CUDA or cuDNN libraries, or that you're starting a new project and you need, new versions of those libraries, or whatever the case may be. You're going to hit issues manually setting up CUDA and cuDNN yourself. So that's benefit one, is that you get Ubuntu with CUDA and cuDNN all set up, and it's all running inside of a guest Docker container, plus all the pip packages and environment setup, etc. Benefit two, it's running as a guest inside of your host operating system. So you get to pick your desktop environment. You're not constrained to using Ubuntu as your host operating system, as your desktop environment. Me personally, I'm running Docker for my machine learning projects on my Windows host operating system, which now allows me to play video games, virtual reality, and I don't have to dual boot, and I have access to my GPU through the Docker containers. Now, a little aside, if you want to run Docker on Windows, if you want to run machine learning projects which have access to the GPU on your host Windows environment, you actually have to switch to what's called the dev channel of Windows. You go to where you'd normally check for updates in Windows. Somewhere in there's a place where you say, I want to use the dev channel of Windows. It's basically like beta. It's asking to use Windows beta, which is a little bit scary, but I won't say it doesn't come with problems, but the problems are well worth the ability to access GPU through Docker containers, in my opinion. I've been using this Windows Insider channel / dev channel for a good year now, and I've only hit like a minor snag in that process. And then what you do is there's some setup instructions. Maybe I'll link them in the show notes. You install an NVIDIA driver, which is specific to this dev channel, and NVIDIA Docker, and then now your Docker containers have pass-through access to your host system's GPU. And in my case, this is fantastic because I can run some background machine learning jobs in my Docker container using the GPU, all while I'm doing some other programming task on my host operating system for some other client. Now, if you're using Mac, you still are limited, unfortunately, because newer Mac models, MacBook Pros, for example, don't come with NVIDIA graphics cards. They come with AMD graphics cards, which don't have CUDA, cuDNN, and therefore you'll have to go through some roundabout methods to write your machine learning code for accessing which use the GPU. Like there's this library called PLAD-ML, which lets you access the GPU. I think through TensorFlow and PyTorch. I think it might be a layer that sits between. I'm not sure. And it's like it's supposed to be GPU brand agnostic and whatnot, but you're going to have to jump through hoops if you're using a Mac. And so for this reason, I recommend machine learning engineers stick to PCs, Windows or Ubuntu. And recently, because you can now use Docker containers on the Windows dev / insider channel, which can access your GPU, I would recommend using Windows. It's, in my opinion, a little bit better of a desktop environment than the Ubuntu desktop environment, and allows you to do some of the other stuff software compatibility-wise, like gaming, which Ubuntu doesn't do quite as well. Okay, benefit number one, end-to-end system setup on your behalf. Benefit number two, you can use whatever host you want, be it Windows, Linux, or Mac. And finally, benefit number three is when it comes time to deploy your machine learning model to the cloud. We were talking about using Amazon EC2 instances and setting these all up with Anaconda and all that stuff. You don't do that. You deploy your Docker file. You literally just deploy your Docker file, and it sets up your entire end-to-end server for you, replicating your environment, including code, open ports, and all those things. It's just snap. You have your entire system now replicated in the cloud, all with the push of a button, because you maintained a Docker file which manages your local Docker guest container. Now, the way that works is thus: if you're making a machine learning server, if you're making a machine learning model that's intended to be ran on a server, if it's a long-lived server, then you have two options. One option is to use Amazon Container Services, ECS. And I'm talking specifically within the AWS stack here. I'm most familiar with AWS and less so with Google Cloud Platform, GCP, or Microsoft Azure, or any of the other platforms. Most familiar with AWS. So in AWS, you could deploy a long-lived machine learning model, something that's intended to just always stay on. You could do that in ECS, Amazon Container Services. And the reason you do it there rather than EC2, the traditional deployment model for AWS server instances, is that ECS is a Docker product. It's a product that is intended to take your Docker file and run a server from it. And you have control over these instances, what are called services in ECS. Services run tasks, and then tasks have task definitions. These task definitions are where you specify where is the Docker file located. Is it on Docker Hub, or is it over here in the Elastic Container Registry, ECR? You can host your Docker file wherever you want. Where do I find this Docker file? What are some of the ports I want open? And what are some of the environment variables like secret keys and stuff like this? So you'll specify those in the ECS UI, and then it will just run the server for you automatically because it has the Docker file, which tells it everything it needs to know to run the server from end to end. So that's ECS. Another option available to you is SageMaker. Amazon SageMaker allows you to deploy trained machine learning models to a REST endpoint. Now, it's not really Docker-centric. It maybe lies outside of the purview of this episode. But basically what you would do is you'd train a machine learning model like TensorFlow or MXNet. You train a model and then you deploy it to SageMaker, Amazon SageMaker. And then now what you have is a running instance of that model that can take data, rows, that you pass it over a REST endpoint and return the results, the inferences, the predictions. Now, what does that have to do with Docker? As far as I understand, I think it is compatible with Docker. I could be wrong on this. My thinking was that if you have other requirements than what is provided by SageMaker's default dependencies, that you might be able to use Docker to kind of orchestrate the provisioning of that setup, but I may be wrong. But overall, ECS is kind of your go-to for deploying a Docker container. And there's one more option, and that is if your jobs are not long-lived, if they're short-lived, or at least they're intended to die eventually with an exit 0 in Python, or they just run a Python file and then eventually it just stops. Like for example, training a machine learning algorithm. Typically what you'll do is you Python train.py, and it does its thing, and eventually it reaches the end of the Python file, and that's it. It's over. The script ends, and you're back in terminal. Well, what you would do is you can deploy your Docker file, your Docker container, to AWS Batch. These batch jobs allow you to run one-off container runs. You specify which file it intends to run in the Docker file. It's called the entry point directive. So Python train.py, for example. And then you set this up on AWS Batch, and you kick off a job one way or another. You can do it through the AWS website, or you can do it through an API call, Bodo 3, in Python, or some service can actually kick off a job, and it will run that job until that job completes, and then it will come down. It will come back offline, and therefore you're no longer being charged for the compute resources of the very expensive GPU instance that it's running this code on. And the minimum GPU AWS instance available to Batch is going to be the P2 X large instance. That's a NVIDIA K80 GPU. I mean, that's pretty much the minimum GPU you'd want to be using for machine learning applications these days anyway. So it's a good minimum to work with. But what batch lets you do is specify that you would like to run these batch jobs on a spot instance if available. And then if not available, you can either just wait until one is available, or you can run it on a normal instance. And a spot instance is a fraction of the cost of a normal instance. So if you're running your P2X large, your machine learning job inside of a Docker container on a P2X large, and it just so happens to be able to nab a spot instance because you told it to through batch, then it could cost you 1/10 of the price that it would normally cost you to run an ECS instance, long-lived ECS instance on a normal P2X large instance. So these batch jobs are fantastic. I use them for Nothi, and in fact, I use them for actually long-lived container runs, not just short-lived. What I do is I have a loop. I have a listener loop, a while loop that is looking for new jobs to run on behalf of users. If they're going to run a summarization or a question answering or create a new entry, and it kicks off these recommending the books job, it listens for any new jobs that may have come from a user. And if there's been nothing in 15 minutes, then it does a Python exit 0. And then batch sees that exit 0 and then shuts the whole thing down. But as long as people are keeping it active, as long as there's activity every 15 minutes, it never hits exit 0. And so that batch job is effectively a long-lived instance as if it were running on ECS, but with an added benefit that I can use the spot instances. So Docker. Those are the three big benefits of using Docker. Instead of Anaconda, instead of a standard Python installation on your local host, the three big benefits are: 1, you can run it on your host environment. You can run any number of Docker guest containers on your host environment at a time. They'll only request the resources they need, and therefore you don't have to worry about the state or setup of your desktop development environment. You do your own thing with your computer that you want. Docker containers come and go. You might be working on a project here. You can forget about it next month when you're not working on it anymore. It didn't touch your operating system. You could play your VR games on your Windows machine and run these Docker containers in the background. Number 2, they do all the setup for you, all the setup from A to Z. The installation of the operating system, the installation of CUDA and cuDNN, the installation of TensorFlow, PyTorch, and all these pip packages. And I haven't mentioned this yet, but there are NVIDIA Docker files that you can inherit from. NVIDIA Docker files on Docker Hub that you you say in the Docker file, at the top of your Docker file, you'll say from NVIDIA /CUDA 10.1 cuDNN 7. You can inherit from Docker files that have all these machine learning libraries set up for you, tried and true. Everything's known to work with each other. All the versions match and all that stuff. So you don't have to go through that process yourself. In fact, you could pretty much do nothing in your Docker file. If you're worried about there being a learning curve learning Docker, you can get started using Docker, using an empty Docker file that just inherits from one of these Docker files that have all the packages set up for you. Popular ones are going to be NVIDIA's own Docker files. Like I said, that sets up CUDA, cuDNN. And then the Hugging Face Transformers Docker files actually set up TensorFlow and PyTorch versions compatible with CUDA and cuDNN and compatible with, of course, the Hugging Face Transformers libraries. And I myself have made a couple of Docker files. These are under GitHub /Lefnir, my handle, /ML tools, ML-tools. There's a Docker files folder, and these are kind of like the kitchen sink setup. It sets up CUDA, cuDNN, PyTorch, TensorFlow, Hugging Face Transformers, UKP-Lab, Sentence Transformers, and then a whole bunch of helper libraries, scikit-learn, pandas, numpy, blah, 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 blah. If you just really want to get started on machine learning engineering on a local host, you don't want to have to worry about anything, use one of these Docker files, because it'll just set everything up for you, and then you don't need to worry about what you may or may not need. So benefit 1 is it's siloed from your host environment. Benefit 2 is it sets everything up for you, even more so than Anaconda, which is already a step above Python raw. And then benefit number 3 is that as you go along maintaining your Docker file and your environment and your code, it's all going to be kept up to date. If you need new software in your guest environment in order to do something new you have decided to do, let's say you need, I'm actually going to use a database. I'm going to install Postgres 12 and pip install scicop G2. Suddenly you needed a database. You modify your Docker file. You have to modify your Docker file so that you can rerun the Docker file to install these dependencies. Well, now your Docker file is up to date, so if you run this now in the cloud, it's always up to date. So Benefit number 3 is your Docker file is the source of truth, and now you can take that Docker file and you can run it all over the internet. It's portable, and it just automatically sets up servers wherever those servers may be. They could be on Amazon SageMaker, they could be on Amazon ECS, Amazon Fargate, Amazon Batch, okay, the Kubernetes offering, Amazon Kubernetes. So that's all AWS. These are all different products in AWS that support Docker. And then Google Cloud Platform, the inventor of Kubernetes, which is a Docker-based project. I'm not going to talk about Kubernetes here, but GCP obviously has mega first-class support for everything Docker because, like I said, they are extremely involved with Docker. The future is Docker. The future is Docker. All these cloud providers, I'm telling you now, they're going to move off of running your own servers eventually. So you're going to have to learn Docker eventually. Might as well be now because it will save you so much heartache on environment and software setup. So learn Docker, use Docker, stop using Anaconda, unless you're using it inside of your Docker instance. I mean, there are reasons to use Anaconda, but not as a primary way to silo environments on your host environment. And yeah, deploy your Docker containers to the cloud and save yourself some trouble. That's it for this episode. I'll see you guys next time.